electromotive force EMF or E of an electrical source such as a cell, a battery, or power supply is defined as the electrical energy U received by 1 coulomb of electric charge Q after passing through the source. That is, if the EMF of a cell is E equal to 3 volts, then when 1 coulomb of electric charge passing through the cell will bring out 3 joules of electrical energy, U equal to 3 joules, when passing through the cell from the terminal X to another terminal Y. Remarks 1. In an electric circuit, the conducting charges are electrons. Second, electronic charge E equal to 1.6 times 10 to the power negative 19 coulomb. Finally, 1 coulomb of charge represents 1 over 1.6 times 10 to the power negative 19 electronic charge. When there are Q coulomb of charge passing through the cell, the energies brings out by the charge will be U equal to Q times E. This equation is important. Then what is potential difference, PD or V? Potential difference across an electrical device or appliance is defined as the energy converted from electrical to other forms of energies when 1 coulomb of charges passing through it. If the potential difference or the voltage V across a bulb is 3 volts, that means when 1 coulomb of charge passing through the light bulb, 3 joules of electrical energy will be converted to heat and light energy. That is, if the energy conversion is E pi and the charge is Q and the voltage or potential difference is V, then these 3 terms are related by V equal to E pi over Q. Or we say E pi equal to Q times V. Let's complete the table. Voltage across the bulb is V, charge passing through the bulb is Q, energy conversion is E pi. For the first row, we have E pi equal to 1 times 2 equal to 2 joules. Second, E pi equal to 2 times 5, which is 10 joules. For the last one, E pi equal to 110 times 6, which is 660 joules. By energy conservation, we say the total EMF of a circuit is equal to the total potential difference or the total voltage. In this example, if the EMF of the circuit is E and there are 2 light bulbs here, for the first light bulb the voltage is V1 and for the second light bulb the voltage across it is V2, then we have a relation between E and V, which is E equal to V1 plus V2. Electric current I is defined as the rate of charge flow Q over T. That means I equal to Q over T. Example, Q is 1 coulomb and T is 0.5 seconds, then I current equal to 1 over 0.5, which is 2 the unit of I is coulomb per second, or we say equal to 2 ampere A. For the second example, Q is 0.3 coulomb and time is 1 minute. Therefore, the current is equal to Q 0.3 coulomb over time 1 minute times 60 seconds. Therefore, it is equal to 5 times 10 to the power negative 3 coulomb per second, or we say equal to 5 times 10 to the power negative 3 ampere, or we can even say equal to 5 milliampere. 1 milliampere equal to 10 to the power negative 3 ampere. Remarks: inside an electrical device, current flows from terminals at higher electric potential to lower electric potential. In the circuit, we see that this is positive terminal and this is negative terminal. Current flow from higher potential means current flow from the positive pole of the source towards the negative pole. This is the direction of current. How to measure the current flowing through an electrical appliance? In order to measure the current passing through the light bulb, we should connect an ammeter in series with the light bulb. Therefore, the current I can be registered or recorded by the ammeter A. Then, how to measure the potential difference or voltage V across an electrical appliance? In order to measure the voltage across the light bulb, we should connect an voltmeter in parallel to the light bulb. Therefore, the voltmeter reading will be equal to that voltage across the light bulb. We have an experiment to find the ratio of voltage V to the current I in an irregular wire. We use the circuit symbol, the dry cell, a switch. This is the irregular wire, and this is the rheostat, and the ammeter and voltmeter and some connecting wires. First, we connect the DC source, the switch, the ammeter, the irregular wire, and the rheostat in series. Then we connect the voltmeter in parallel to the irregular wire. Now, the ammeter will measure the current passing through the irregular wire I, and the voltmeter will measure the voltage V across the irregular wire. And the rheostat is used to adjust the current. For an irregular wire, the variation of I against V is a straight line passing through the origin, which implies that current is proportional to the voltage. Now, if we change the graph from I against V to V against I, the result still applies, which is I and V are proportional. Therefore, V is proportional to I. And the slope of the graph V over I is a constant value, and we call the slope the resistance of the Eurechian wire. Therefore, for an Eurechian wire, the resistance is equal to voltage over current, and the ratio is resistance R equal to voltage V over current I. The unit of R is equal to volts per ampere, or we say ohm, with symbol equal to this one. For any conductor that has a constant resistance, that means the resistance is independent of the voltage or current, then we say this kind of conductor is ohmic conductor. And for all ohmic conductors, it obeys the Ohm's law, which is R equal to V over I. Notice that not all conductors or not all electrical devices obey Ohm's law. That is, not all electrical device has a constant resistance. You will learn this later.